And then we have our 5 and 45 degrees. So now we need to find what is tangent of 45 degrees. What do we find that to be from our previous work? Yep, that would be 1. You got it, Joel. Tangent is going to be 1. And so here we just have 5 times 1, or just 5. It's going to be 5. All right, so let's go through a few more of these, and then we'll take our break after this. So tangent, 4 times tangent x squared. We'll do this one and maybe one other. Again, the solutions here are going to be for all these parts, so we'll just do at least 1 or 2 more here. So let's go for this next one. We have 4 times the tangent of x, but now tangent x is 30 degrees. We know that that's 30 degrees quantity squared. And again, if we considered the table that we created before, tangent of 30 degrees is going to give us square root of 3 divided by 3. And then we're going to square everything here. So now let's consider kind of each piece squared. So if I have number inside a squared quantity, I need to go in and square each of those quantities as I go. So let's work that out. If I square the 4, that gives me 16. If I distribute that square to the square root, I'll just get square root of 3 squared is 3. And then if I square the denominator, that 3 becomes 9. So I'll have 16 times 3 divided by 9, because I'm going to be squaring each of those 3 numbers right where they're at. All right, and then last but not least, looks like we can, let's keep it the same color, I don't know. Let me fix that color real quick. Everything turned really bright. There we go. If we go back to our work here, just doing a simplification here would be helpful. So 3 and 9 become a 3 in the denominator. And so our final result here is just going to be 16 over 3. All right, so let's do maybe one more, and then we'll take our break. And maybe I'll just jot down the solution for the next one over the break. So we have sine of 90 minus x, and then plus cosine x. So let's start with that sine. We have the sine of 90 degrees minus x here again is 30 degrees. And then we'll have the plus cosine of 30 degrees. So we really have sine of 60 plus the cosine of 30. Now, if we remember our cofunctions, I think these two things are the same thing. And what do those two things happen to be?
Root 3 over 2.
Yep, those are both going to be root 3 over 2. Excellent. So we have root 3 over 2 plus the same thing, root 3 over 2. And so if I add those two things, get 2 root 3 over 2, or just root of 3. We just have root of 3 there. And looks like we'll have time here. Let's do this last one as well before our break. We're going to be working with y, so the 45-degree angle. So let's simplify that last one. We have 2, or negative 2, tangent of 2 times y. Y, again, is 45 degrees, minus 60 degrees. If I simplify there in the tangent, what's the new angle going to be sitting inside there? That would be 30 degrees. That's correct. We have 30 degrees. And so our tangent of 30 degrees, I think we solved that earlier in the previous problem, or the tangent of 30. We did tangent of 45, but we do have, yeah, we did right up here, tangent of 30. We know that to be that square root 3 over 3. Yep, and so we can just multiply and get to exactly, Joel. So we have negative 2, and then it'll be root 3 over 3. And so that's simple as math. We'll just leave it like that. Okay. Excellent work. So let's take at least let's go maybe 7 minutes or so. We'll come back at about 8:03 or so, or 9:03, and we'll begin with the next. So we'll jump into section 2.2 when we come back. Go ahead and stretch your legs, and you can get off the computer for a little bit. See you guys in a few minutes.
Excuse me, Mr. Coughlin, I have a question if you don't mind.
Sure, yeah, go ahead.
For the problem we just did on B, how did you get a 1 from sine 90?
Yeah, so this is kind of I guess, a preview to what we're going to be talking about in chapter 3. So the unit circle would tell us that the sine of 90 is going to be 1 based on the position it's in our unit circle, or just the coordinate plane. So the cosine of an angle is always represented by the x-coordinate, and the sine is always the y-coordinate. And so in our unit circle, when we reference 90 degrees, that point up at the top is always going to be 0, 1, meaning that the sine of 90 is 1, and the cosine of 90 would be 0.
Oh, okay. Thank you.
Yeah. So it's something new. That is definitely something new for us, but it's kind of a preview of what we'll see more of in chapter 3.
Okay, cool. I was just a little confused by that part.
Yeah.
Thank you.
All right, welcome back from our break. We are going to start up into 2.2, so you guys can give me a thumbs up if you are ready to go and are listening. And we will get started here. Excellent. So 2.2, we are going to be looking at some calculations with the acute angles and also looking at these, a different way to measure angles, working in degrees, minutes, and seconds. So let's consider kind of definition to start. So angles are measured in degrees and minutes and seconds. So those are kind of fractional degrees. Each degree contains 60 minutes and each minute contains 60 seconds. So if I considered a few of writing angles, we could say that 50 degrees minutes and seconds can be written as this first one. So we have 1 apostrophe for the 10 minutes and 2 for the 36 seconds. Another example, just 107 and 20 minutes. So let's just do a little bit of angle calculations, just arithmetic ways. If I wanted to perform addition and subtraction with these fractional minutes, we can take a look at adding or subtracting based on our degree measurements and our minute measurements in this case. So if I added 24 and 87, what would be my full degree sum there be? If I had 24 and 87.
111.
Okay, so we'd have 111 degrees total. And then if we added our partial degrees, that would be 33 minutes and 42 minutes. How many total minutes would we have there?
75.
Okay, 75 minutes. Okay, but notice that 75 exceeds our 60-minute to a degree ratio. And so we want to be careful about that. We really have over a degree here to work with. So this is really 1 degree and an extra. Oop, I did the wrong. Let's do the right measurement there. 75. 75 minutes, we could say, is 1 degree plus an extra 15 minutes. Because again, each degree is 60 minutes. And so we can sum this up and say we really have 112 degrees in total if we add both of those, and 15 minutes left over. So that would be our final result, 112 and 15 minutes. All right, go ahead and take a moment to solve part B here. Yeah, question?
Yeah, what is that dash on top of 42 called?
So this dash is just the minute symbol. That's just to designate that that's a minute.
Gotcha. Okay.
Yep. So let's go ahead and you guys want to try part B here with this subtraction. If you guys find a solution, go ahead and put that into the private chat to the host, if you will. We'll do that. I'll give you guys a few minutes to work out the solution for part B, and then we'll take a look at it together. Awesome. Got yours, Layla. And Eduardo got yours as well. Nice job, Amanda. All right, so notice here we are subtracting these two angles in part B. So we do want to subtract each of their components away from each other. So if I started with 71 full degrees and subtracted the 55 degrees in blue here, we would end up with just 16 full degrees left over. And Fernanda, did you have a question there?
Oh no, sorry, that was automatic.
Oh, no problem.
That was the system. So
And if we take a look at the minutes, the fractional minutes here, subtracting those, 46 minus 21, I think you'll find that to be 25 minutes. So there we have it, 16 degrees and 25 minutes. And I think that would be our final solution. So we can leave it just like that. Be good to go. So the next thing that we might want to be doing with these degrees and minutes is converting them between degrees and minutes and decimal degrees. And that's what we'll
Wait,
do
that was our
in
final
this.
solution?
Yep, it would be.
Oh, on top, how do we get the 112 again? And the 15?
Yeah, so the 112 came from this guy right here. 75 minutes is equivalent to 1 degree and an extra 15 minutes. Because again, 1 degree is the same thing as 60 minutes.
Oh, okay.
So let's take a look at the next section. We're going to be doing some conversions. And again, this conversion is going to be helpful for us in this next section, 1 degree to 60 minutes. All right, so we're going to be converting angle measures from minutes and decimals. So we'll start with the decimal and go to the degrees and minutes. So I'll do one example here and I'll have you guys try one. So if I considered 62.35 degrees, well, we know that 62 degrees is a full degree. So right off the bat, we can consider that 62 degrees is going to stay in our calculation. We're not going to try to mess with that when we convert to degrees and minutes. But we do want to work with the 0.35 degrees. So if I considered working with 0.35 degrees, I know that when I convert this 0.35 degrees, each degree, 1 degree here, is equal to 60 minutes. So I'll set up a ratio here to change those units from degrees to minutes. So we'll notice that the degrees, those units will cancel with that ratio. And now we just need to multiply across with 0.35 and 60. So if I do so, what value am I going to get after multiplying across here for that conversion? And you're right, 21 minutes. 21 would be the calculation there. So this would be 21 minutes. And so that decimal, we can then just add back to our beginning 62 degrees. So we can write that as 62 degrees and 21 minutes. All right. Is there any questions with part A there? Okay, go ahead and take a moment to convert part B. I'll give you guys a few moments to do so. And you're welcome to put your answer in the private chat if you want to get a response either way. Okay, got yours, Eduardo, Fernando. Alec, got your response. All right, so let's remember here that we are just working with that decimal degree. So we don't have to convert that 27. We're just converting the 0.8. So if I started with 0.8 degrees, again, we're going to be using that same conversion factor, 60 minutes to 1 degree. If we end up multiplying through with that conversion ratio, what, or I guess, there we go, minutes there, what would be our minute calculation with that? We multiply across there. 0.8 times 60. Anya, you got it? Yeah, 48 minutes. And so we can attach that to the existing 27 degrees. And that would be our solution. Any questions with that conversion in that direction, degrees to minutes? Right. Just going in the opposite order for a couple examples here. We wanted to convert each angle to decimal degree. We're going to do a very similar calculation. Again, the whole number we're not going to work with at all. 35 is going to be the whole number degree. And we just want to convert, and then I think I didn't want to do seconds here. So let me change these. This would just be a minute there. So you can change that in your notes as well. I forgot to change those. So just make those a minute calculation. We'll go to work with these. So 35 degrees is our whole number. I wanted to convert 45 minutes over 1 times. We'd want to just really use the opposite or the reciprocal of our conversion ratio from before. That would be 60 minutes on the bottom is equal to 1 degree on the top. And if we multiply through with this, 45 divided by 60, I believe you're going to get a decimal result for this to be 0.75 degrees. So that would be 3/4 or 0.75.
So why is 60 at the bottom now?
Yeah, because we're converting in the opposite order now. So I'm starting with minutes at the top, and so I need the minutes to be able to cancel with the degrees. So the degree measurement, or on that ratio, 1 degree is still equivalent to 60 minutes, but I need to make sure that it's lined up so that those minute units would cancel. So we just set it up in the reverse order because we're going in the opposite direction.
Okay, thank you.
Any other questions? We have a, yeah, go ahead.
Hey, so let's suppose that actually instead of minutes, we deal with seconds on how do we resolve on the second thing?
Right, yeah, so if it was seconds, we can resolve that. So if it was, say, 45 seconds and we had a double, and I don't think you'll have to do this necessarily in your homework, but we can talk about it. So this would be, if we wanted to do this to a decimal, we would just have to take this and say 60 seconds is equal to 1 minute. So that would be our first conversion. And then we could go and say 60 minutes is equal to 1 degree. So we would really just divide by 60 twice to get the decimal that we wanted. So we certainly can still do it, but I think my intention was just to use the minutes there. So it's very similar to if you were to write how many seconds are in an hour. It's a very similar calculation with those units. So the final result is going to be 35.75 degrees. All right, so let's just do one more together, and then I think we'll have a live problem to work on here. Again, with 77 degrees and 25 minutes, we'll go with here. We'll have 77 whole degrees, so we don't have to work with that at all. We'll just work with the 25 minutes. So 25 minutes over 1 times our conversion ratio. If we do 25 divided by 60 here, what is the decimal result going to be there? Joel, you got 0.41. I think you'd be right there. We do 25 divided by 60. And again, this thing round to the nearest hundredth. So really 2 decimal places here. We should end up being approximately 0.42. That would be in degrees. Again, our units here for minutes would cancel, and we'll just be left with 0.42. So we can write that as 77.42 degrees. All right, let's take a look at a few questions here. We'll actually just start with number 2, and we'll run through 2 live questions here as we go. So I'll open up number 2 to work with. We'll find the exact value for the following cotangent of 45 degrees.
Is this the live assignment?
Yep, this is in the live assignment number 2, if you want to jump into that. Yep, Joel, you would be correct there in the chat. That would be equivalent based on our cofunction ideas. Yep. So let's see what results you guys were getting here. Everybody got 1. That's good. All right, excellent. So this one is exactly 1. Remember that cotangent, we can think of it 2 ways. We could either think of it, cotangent is the reciprocal of cotangent. So tangent of 45 degrees we found is 1. And so if we take the reciprocal of 1, it's just going to be 1 again. Or Joel pointed out here just by cofunctions that cotangent of 45 is equal to tangent of 45, just because of the cofunction nature as well. So either way you think about it, this is going to be equal to 1. So that's good. So let's take a look at a second problem. The last one we'll do a conversion problem here. All right, looks like we got a good collection of solutions here. So we'll see where everybody landed on this one. Okay, 60 degrees and 33 minutes. I think that would be correct there. So when we convert the 0.55 degrees, we're really multiplying by 60 to get the seconds calculation. So we should get 33 there. We can close that out. That should be the correct solution. Sometimes the live assignment doesn't give the correct thing right there, but correct solution there should be 33. So you guys should have that. Go back to your notes. Oops, converted. That's okay. We'll just start on this guy now. All right, so the next thing we'll do is just to get used to the sine, cosine, tangent buttons in our calculator. We're just going to work with evaluating a few of these and just rounding to the nearest hundredth. So just as some practice with our calculators, let's go with part A. If we were to take cosine of 42.5 degrees, go ahead and try that in your calculator. We'll want to round that to the nearest hundredth. We'll just run through these fairly quickly. What do we end up getting for the cosine of 42.5? And this is a good check to make sure that our calculator is in degree mode. So we want to be in degree mode. So if you're not in degree mode, you might get a really small result here in radians. So make sure that we are in degrees. Yeah, so question about putting it in degree mode. It depends on what calculator you have. If you have a TI 84, there should be a mode button on the top of your calculator. Or that, yeah. So if you have a Casio, it'll be a little bit different. I can definitely walk you through it. Second 0 would be that for that one. Okay. So I think if you are into degrees, you should end up getting approximately 0.74 for this. So if you're ending up getting that, you are in the right mode. If we were to go find the secant of 78, what would we have to actually represent that as? What's another way to write secant of 78 that would be helpful for us? Sam, you're right. Yep. Close to that. This would be 1 divided by the reciprocal function there is the cosine of 78. The reciprocal for secant is cosine. So this is 1 over cosine 78 degrees. So if we try 1 divided by cosine of 78 degrees, cosine is in our calculator, so we can use that. What do we end up getting for that ratio? Anya, I think you've got it, 4.81. 4.81. You can confirm that in your calculator with that one, 4.81. How about going up to part C? We have the tangent of 23 degrees. Again, we have a tangent button, so we don't have to really convert that at all. We're in degree mode here, tangent of 23 degrees. What would we find in our calculator? There you go. Yep. You guys are all on the mark there, Annabelle and Anya. Joel, you got it. So 0.42, approximately 0.42. And then the last one we have on our list, cosecant of 54 degrees. Cosecant, yep, that would be the 1 over sine, exactly. Now we're going to use 1 over sine of 54 degrees. We want to take that ratio. And yep, that would be good. So 1.24. 1.24. All right, so let me pause here. Is there any questions? Is everybody kind of figuring out their calculator as we go here? Joseph, you have a hand raised there.
I'm sorry, I just had a question on how you were able to find the reciprocals.
Yeah, sure. Yeah. So if we think of it in general, there's a couple ways we can think about. So if we go back to part B, so a couple ways we can write the reciprocals. If we just had a general angle of theta, this is equivalent to 1 over cosine of theta, or we could write cosine of theta is equal to 1 over secant theta. So that's just the definition for those reciprocal functions. And we're just naming what angle we want theta to be.
All right, but like, how do you know that cosine or 1 divided by cosine of theta is the reciprocal for secant of theta?
That's just the definition of what secant means. So that's just a given definition of trigonometry.
All right.
That doesn't seem satisfying.
Yeah, sorry. This is all kind of like, I wouldn't say new, but like when I was originally learning
Yeah.
about the sines and cosines, I struggled with learning about these, so I'm still a little bit behind. Like I'm still
Okay.
struggling.
Yeah, so this is just the, I guess, the elementary building blocks of what those definitions of those functions mean. Just like when we say the cosine means adjacent divided by the hypotenuse side, it's just the definition of how we name things.
Okay, okay. I'm gonna have to do some review, but thank you.
Any other questions before we continue and we look at maybe some inverse trig functions as we go? Okay. All right. Just have a little bit longer here, and then we'll kind of go to questions for the day before. The next thing is going to be kind of working with some inverse trig functions to solve the following expressions. So inverse trigonometric functions can be used to find the angle measure of a given trigonometric ratio. So let me do a little bit of a talk before we get into these problems about what is exactly going on with an inverse trig function. So to start, let me just use the sine function just for an example, but it works with all of the other functions. So if I had a sine of theta, and I'll just say sine of theta equals, opposite over hypotenuse, just for our general definition. So remember that theta here, when we have a sine function, theta is an angle, and it outputs a side ratio. By definition, it just takes in an angle as an input, and it gives back a side ratio as an output. Okay, so that's our basic sine function. Now, if I think about an inverse functions swap the inputs and outputs. So when I consider the sine inverse function, this is how we would write sine inverse. We input a side ratio, I'll just call it O over A, H. I input a side ratio, and sometimes this is just a single number as a decimal because we reduce it as just a number. And this outputs some angle theta, which is an angle. Okay, so when we solve for an angle, what we're really doing, or using a inverse trig function, is we're solving for an angle with a specific side ratio that we know. So again, the roles are reversed when we do an inverse trig function. And so we're going to be using these inverse trig functions in the next section, but we just want to have a foundation of what exactly are we finding when we're using this inverse trig function. We're solving for some value theta, which is an angle. Okay, is there any questions with just that basic approach of inverse functions, swapping inputs and outputs? Sure, yeah, go ahead, Fernando.
I mean, probably this is like way advanced, but like the -1, is there a possibility, or is there a scenario where it's another number, like sine -5 or no?
No, so yeah, that's just a symbol denoting the inverse function. So if you look on your calculator, you'll see like cosine to the -1. That's just a symbol of writing the inverse function. So it's just a symbol of mathematics. There's not going to be cosine to a -2. That wouldn't be a thing. Another way you could write an inverse function, you'll see this in our notes later on also, is arc sine or arc cosine. So those naming technologies are the same thing. That naming scheme is the same thing as sine inverse or cosine inverse. So we'll get to that, but those two things would be the same thing. All right, so let's jump into this first example, and then we'll get to the rest as we go. So we want to find the acute angle theta for tan theta equals 152. So we have really what we would call a angle theta. Remember, this is our angle, and this is our side ratio. So when I consider finding that angle, what I need to do is take in this case, a tangent inverse to kind of undo that tangent function and find theta. So a way we can write this out is to solve for theta with tangent inverse of my side ratio. My side ratio here happens to be that number 3.152. And again, this is going to be equal to theta if I solve that correctly. So again, if we're in degree mode, we'll try to work this out. If you want to do the tangent inverse, you'll have to do the second and then hit our tangent button, second tangent. And that will give you the tangent inverse to input your side ratio. So take a moment and put in our tangent inverse, so second tangent, and then type in our side ratio. And I'll confirm the solution that I have here. A moment there, and if we end up putting this into our calculator, I think Annabelle, you are right on. We round to the nearest tenth of a degree. Yep, Joel, you've got it too. I think we end up getting 72.4 for theta. So theta is equal to 72.4 degrees. That looks great. All right. Let me give you guys a chance to do the next one here. We have an acute angle A for which cosine of A is equal to 0.921. So I'll give you a moment. Let's solve for that angle A, again, round to the nearest tenth of a decimal. You can put it in the private chat if you'd like with your solution there. Okay, got yours, Joel. Layla. Amanda got yours. Alec, I got yours as well. Annabelle, thank you. Awesome. So if we were to calculate this angle A here, we could set up a inverse function for the cosine inverse in this one of 0.921. And it looks like we are getting a common result there. So this is going to be 22.9 degrees. All right, the next two that we're going to do need a little bit more work to solve. So we'll try to walk through these a little bit slower, starting with a cotangent function. So number 3, if I have an angle B, this is going to be a cotangent B equal to 0.857. Well, the first thing we want to be careful about here is we don't have a cotangent inverse, right? So we have to find a way to navigate not having a cotangent inverse, but we do have a tangent inverse that we just solved with. So one way we can think about this is if I wanted the tangent of B, I know what I could do with the tangent of B. And these are going to be the reciprocal functions. So if I said the tangent, that's going to be just the reciprocal of the cotangent ratio. So this would say the tangent ratio is just going to be 1 divided by 0.857. They're reciprocals of each other. The tangent of B is just 1 divided by that ratio. Now we have something that we could set up with a tangent inverse. So here I could say that the angle B is equal to, now I can use my tangent inverse instead, and I'm going to put 1 divided by 0.857 in that ratio. So the first thing we had to do again is take the reciprocal, because we need the reciprocal function tangent, and then we're going to use the tangent inverse. So you guys can find what that would be if we do our tangent inverse for that. And I think you guys are getting it, Annabelle and Anya, 49.4 degrees. That is looking good. So watch out for those reciprocal functions. We have to have kind of an extra step in there to convert to our reciprocal ratio and then use our inverse function. To give you guys a minute to do the last one, number 4, using the cosecant of C. To give you guys a minute to do that. If you'd like to drop your answer for this one in the private chat, that would be great. Give you guys a few minutes to find angle of C. Got yours. Let's see. Sam, Eduardo, Amanda, Layla, Fernando. Awesome. Clayton, got your response. Joel, got yours. Excellent. Looks like we're narrowing down to the same solution there. Again, if we have the cosecant, what is the reciprocal for cosecant?
10?
Yep, sine. The sine function. So we could write an equivalent statement, the sine of c equal to 1 divided by 1.261. That's the reciprocal function. And so we can do ALC is equal to the sine inverse of our argument, 1 over 1.261. And it looks like you guys were getting 52.5 degrees. And I would agree with that. The 52.5 would be our final result there. So that's a little taste of inverse functions. We'll definitely revisit inverse functions throughout the course at different times as we progress. But you kind of have a taste of how inverse functions work and the relationship between the inputs and the outputs.